So let's talk about recursive programs. Okay, another application of recursion. So actually the recursive programs implement recursive functions, but what I'm going to show you is how we analyze recursive programs, and in particular, what do they do and how long do they take. Okay, so let's define a recursive program big of n. Okay, big of n. Okay, so what does this this program do? Well, n, think of n. So n is a natural number. N is in n. Okay, so if, or n is in n, is a non-negative integer. So if n equals 0, so sometimes we write double equals for comparison. If n compared to 0 is true, okay, then return your output as 1. If n bigger than 0, okay, so you check if n is 0, you return 1. If n is bigger than 0, return your output is equal to 2 times big of n minus 1. Okay, so let's see what big of n does. So if I plug in n, okay, and so this is always the case when you analyze a recursive function. So here is big of n. Let's see what it does. When n equals 0, it returns 1. When n equals 1, it returns 2 times big of 0. But big of 0 is 1, so this returns 2. If n equals 2, it returns 2. It returns 2 times big of 1, which is 2 times 2, which is 4. Okay. And you can convince yourself that when n is 3, it's going to return 2 times big of 2, which is 8. And dot, 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 dot. So we're ready to make a guess that big of n equals 2 to the n. Okay. And the proof is by induction. Clearly the base case is true, so big of 0 equals 1, which is 2 to the 0. Check. Okay, now I need to show that if big of n equals 2 to the n, then big of n plus 1 equals 2 to the n plus 1. Okay, but that's easy to do. And by now we're familiar with this. Look, so if big of n is 2 to the n, then big of n plus 1. Now this is where we use the recursion, the recursive part of this function. Big of n plus 1 is equal to 2 times, big of n plus 1 minus 1. So 2 times big of n, which is 2 times 2 to the n, because we assume big of n is 2 to the n. Okay, which is 2 times 2 to the n, which is 2 to the n plus 1, as required. So this is because we get to assume that big of n is equal to 2 to the n. So that proves that this recursive function computes 2 to the n. It's a very compact function. Okay, but now, interesting question. How long does this function take to run? Okay, what is the run time? Okay, what is the run time? Now that's the interest. It looks like a very short piece of code, so it looks like no matter what n you give me, it's going to run very quickly. Not so. Okay, so let's try to analyze the runtime when n equals 0. So let's put here, let's call the runtime, let's call the runtime t sub n. So, n being the value of the input. So n could be 0, n could be 1, n could be 2, and so on and so forth. Okay. So what is the runtime? So let's put here n. Okay, let's do n here. N equals 0. And what's the running time? T sub n. Okay, so let's see. When I feed in n equals 0, it does a comparison. Let's assume that all operations, take approximately 1 unit of time. So it does a comparison. Okay, the comparison says yes. So it assigns output to 1 and returns. Okay, so 3 operations. Comparison, assign 1 to output, and return. So 3 operations. Okay. Let's see what's the runtime when n equals 1. Okay. So it does a comparison that fails. Okay. So then it comes here. Okay, and it does another comparison. So that's 2 operations. Okay. Then what does it do? It asks you to compute this guy, but we know that that's big of 0, so that's 3 operations. Okay, so one comparison, a second comparison is 2, 3 operations, and then a multiplication, so that's 4 operations. Okay, and then an assignment, that's 5 operations, plus the 2 that it already did. Okay, that's 7, plus the return, that's 8 operations. 8 operations. This is very complicated. Okay, and now now we can similarly compute the running time for n equals 2. Let's just do it. Okay, so 1 operation, 2 operations. Okay, 8 operations here. So that's 10, multiplication 11, multiplication by 2, 11, assignment 12, 13. So 13. Okay. And if you wanted to, you could do 3 and you would find that it's going to take you 18 operations. Okay. So now let's go and see if we can analyze, okay, Tn. Okay. So Tn, let's see. What's the running time Tn? So the running time Tn is equal to, so if I fed in n, let's see if we can analyze it. Okay. So if I fed in n, I'm going to do a comparison. Let's assume that n is bigger than 0. So you do a comparison, that's 1. Okay, then you do another comparison, that's 2, that's another 1. Okay, then you're going to have to do a multiplication and an assignment. Okay, so that's 4, so that's 2 extra, so plus 1, plus 1. Okay, and then you're going to have to do a return, so that's plus 1. So there's 5 there. Okay, but you also have to compute big of, n minus 1. Okay, and how long does that take? Well, we don't know. So we can't compute it explicitly, but we do know, in some sense, that's going to take the running time for n minus 1. So Tn is going to equal Tn minus 1. Okay, plus 5. Tn is going to equal Tn minus 1 plus 5. So the high-level conclusion is very important, that whenever you have a recursive function or a recursive program now, so a recursive function programmed into a, let's say a program, okay, the running time, analyzing the running time reduces to a recurrence. Okay, so the running time satisfies a recurrence. And now we can try to analyze this recurrence to get the running time. So I ask you to show that the running time, T sub n is equal to 3 plus 5n. Okay, show by induction. Okay. And now look, even though this is a very short program, its running time is increasing with n. Even though the program size is fixed, its running time is increasing with n. In fact, in this case, it's increasing linearly with n. Okay. So now, I'm going to challenge you. Is this the best running time we could get? So I challenge you to come up with a recursive function whose running time is actually increasing instead of linearly with n. I challenge you to come up with a recursive implementation of, exponentiation whose running time is increasing with the logarithm of n. Okay. One can get Tn equals, is approximately equal to log base 2 of n. What approximately equal to is sort of hard for us to define at the moment. And to get this kind of running time, it has to be a slightly different recursive program. It'll still be short, but it has to be slightly different. And you can see if you can figure out how to do it. Okay, we're going to move on.